just describing the connection, who is connected to who in the graph, the vertices, right? And then we have attributes for nodes and edges. The attributes characterize the data that we have, right? So they are features of the vertices and features of the edges. And they are, as you see here, in the more general case, they are tensors. So, right. Okay, so the idea is to play with this type of data, right? And the idea is to use graph neural networks to perform inference on this type of data. And as we will see later, we will use this type of neural networks called graph neural networks to perform prediction of a change in behavior of the system that we are modeling. And we would also like to localize the source of the change, where the change in this type of data that we observe over time is localized, right? And I'll try to provide also a bit of motivation why this is useful in the context of epilepsy. So what are graph neural networks? Graph neural networks are a specific type of neural networks that can process graph structured data, right? So they are neural networks that can process graph. And basically what they do is to take graph as inputs and represent graph in a different way. So they extract a representation out of graph, usually a numeric representation out of a graph given as input. This is exactly what any kind of neural network is doing on other types of data, like for instance, with more conventional vectors, if you want, or with images, or with time series, if we are talking about recurrent neural networks. So it is interesting to look at neural networks as a way to represent in a different way your data, such that the task that you're dealing with is performed in an optimal way, let's say. All right. So, if we want to look at the components of graph neural networks, we can roughly talk about two components. And there is a convolution block and a pooling block. And I'll just go over these details. So I have the time, and let's see how much time I have. So the convolution operation is the first block, and is a generalization of what we know for images, right? So a convolution is basically using a filter on an image, which can be represented as a regular grid, as you see here, and is basically using the information of a neighborhood to process the image and create an alternative representation of the input image, right? So the convolution on a graph works in a similar way, in a totally similar way, but it exploits a generalized version of neighborhood, because we are potentially on a non-regular grid, right? A graph can have any kind of neighborhood, right? Like in this case, we don't have a complete graph. So the neighborhood of each vertex must be taken into account when we perform the convolution. So as you see in this, for instance, representation, the node representation is performed by using the neighborhood highlighted in green. I hope you can see green on the edges of each node, like as you see here, right? And this step of convolution basically represent the signal of the graph or the features of the original graph in a different way. Okay, and in particular is using the information of the neighbors of each node to compute new features. Right. This is same thing expressed via equations, as you can see in this equation, there are three main elements. There is A. A is the structural connectivity of your graph, which can be anything from the Laplacian or normalized Laplacian of the graph, but we can use also other type of structural connections like adjacency and so on. X are the, as you've seen before, are the features, original features, and W's are the weights of the network or the filters that are learned during training, right? So convolution seems to take into account only the features of the nodes, but there are variations of convolution that can take into account also the features of the edges, right? And for instance, in this case, there is one paper which is providing a solution for this. Okay, so both vertex and edge features can be taken into account for the convolution step. Pooling. What about pooling? So depending on the task that we want to solve with a neural network, we need to perform also pooling. Pooling is an operation that reduces the graph, the size of the graph, right? So in supervised setting, we have graph and the targets associated with the graph. For instance, if you want to perform classification, you want to classify your graph, your data will come as a set of pairs where you have graph and labels. And so you have to, at the end, you have to make a decision about globally about a graph, a single graph. You have to classify the graph. So there is a need to perform pooling to reduce the graph and aggregate information, and then at the end make a decision, classify the entire graph. Pooling is doing the reduction, and basically it's just shrinking the graph over and over. And there are many, several approaches that have been proposed. For instance, this one we recently proposed with my collaborators, and is based on spectral partitioning, crown reduction, and sparsification. We don't have the time to go over the details of how it works. If you're interested, you can take a look at the paper there. And so if you want to summarize the functioning of a graph neural network, we have basically, as we said before, a convolution which takes a node and edge features and provide a representation of the graph, an initial representation. And then there is a pooling step where the graph is reduced in size, and this can be repeated if we are using multiple layers, right? And at the end, we make a decision that is related to the task. So if we are classifying the graph, we produce probabilities associated with the graph with respect to the classes and so on. Everything needs to be in the context of neural networks. Everything needs to be differentiable, meaning that you have to be able to use backpropagation, right? And basically that's it. All right, so let's talk a bit about the prediction of future behavior, and let's talk a bit about this project of prediction and localization of epileptic seizures. So we are working in the context of epileptic seizure with a collaborator in Toronto, and the goal of the project is to come up with a methodology to that taken EEGs recording as input is able to make prediction about the onset of an epileptic seizure and localize the source of the onset. And there is also a more challenging goal involving control. So we would like to come up with an automatic strategy to perform neuromodulation, basically, right? So for the first two goals, we already have something, even if we are in the process of publishing or writing a paper. For control, we are still thinking about it. We don't have much to present. We just have ideas. So the raw data that we get come from sensors, and in particular, we have intracranial EEG data recorded on patients, drug-resistant patients that do not respond to drugs. And basically, we have signals, as you see here. We have 128 signals, and we process these signals in order to extract graph. And in particular, we will focus on functional, we will represent the graph in a way such that the functional dependencies between these electrodes are encoded in the graph. All right. So I'll give you some details about the functional connectivity later on. But I'd like to stress the first technical challenge here. So as I said, when we move to a graph, we have let's call it a complex data type that we need to process, right? And we are interested in, at least in this at this stage, in predicting a change in behavior, right? Like the onset of an epileptic seizure. Right. So these in the literature, when we consider numeric data, is known, for instance, as change detection, where we basically analyze the underlying distribution of a process, and we detect or predict when the distribution changes. So when something happens and the data or the system that we are observing is changing, the behavior of the system is changing. So there can be different type of changes in behavior. For instance, like we could have anomalies like a very transient change that lasts just a few time steps, like, or there can be a more permanent change in behavior, right? Like, for instance, a system is evolving, as in operating in a different way, and nothing is wrong with that, for instance. Or there could be a change that is a transient change, but is not instantaneous like an anomaly, right? So epileptic seizures are a type of change, at least we think are a type of change in between a permanent change and a transient change. They are not really like anomalies because the behavior, at least the representation of the behavior of patients changes for a significant amount of time. So when we move to a graph representation of the brain activity, we try to do the same thing. So we try, when we observe graph over time, we try to predict or detect when there is a change in this sequence of graph. So the graph that we are monitoring are changing significantly, right? So it's basically the same problem, right? It's more challenging because the graph are complex data type, right? And we needed, we already worked on detection and prediction of changes on graph sequences. And here you see a couple of references where we face the problem in different settings. At the beginning, we try to approach the problem by mapping graph to vectors and perform detection and prediction on the embedded sequences, and that works fine. But what we're really interested in here is to predict the future behavior of this system, which is represented as a sequence of graphs. So we a more advanced approach will take into account the prediction of graph, not prediction of a change in behavior, right? So we want to get the graph k-step set, basically. And we recently we published a paper here that is basically implementing a conventional autoregressive model, but for graph. So it's basically forecasting a graph ahead in the future. Right. So I think I'll skip these details. Otherwise, we don't have the time to see some of the results. So basically, we can do forecasting on sequences of graph in different ways, and that's nice for the application. And I'll introduce a bit the localization aspect. So we still have to consider the problem setting that I mentioned before. We have intracranial EEGs recording that we convert to sequences of graph that represent the brain activity. And we are interested in three things. For now, let's take into account two of these three things: prediction and localization of epileptic seizures. And we do prediction and localization at the same time because they are, of course, connected. You want to basically find the relevant part of this graph which are fundamental for the prediction, or give you more information about the prediction of the onset. So they are connected, right? And we do it currently. Our solution involves the use of graph neural network with a couple of functional blocks that you see here, convolution, pooling, of course. And there is something called attention, which is basically giving you a weight which highlights the importance of nodes and edges on the graph, and which basically give you the localization of the source of a seizure. Now, there is also something else which is interesting in this context, is the time instants, which are more important for the prediction, right? Ideally, we would like to predict far ahead, let's say, with a given margin, the onset of a seizure, and there might be early warnings of an onset of a seizure, and therefore we would like to highlight also the time instants which are important for the prediction. And this is done with recurrent neural networks, which are, as I said before, a type of neural network that is more focused on temporal aspects of your data. All right. Okay, so we have in place, basically this is the methodological approach that we are following at least right now, and give you some details about how we extract the data. So as I said, we work with functional connectivity networks. We start from raw intracranial EEG data, and we convert this to basically a weighted graph where each edge connection between the nodes encodes the, let's say, the statistical similarity between the two brain areas, which are described by the electrodes of the EEG. And there are many ways to encode this statistical similarity between the brain, brain activity. There, you can go from very simple measures like correlation to mutual information, which takes into account nonlinear dependencies, and you can use phase coherence and so on. You can also rely on a directional measure of dependency, like for instance, Granger causality. And the details right now are not important. The point is that we are encoding the dependency between two brain regions, and in particular their dependency in terms of activity. So we are not using the structural connectivity of the brain to describe the data that the stream of data that we are processing. And so we end up with a sequence of graph of functional connectivity networks, and these sequences are very long. We have recordings that go even beyond 24 hours. So we have lots of graph, lots of data points, and these sequences are also labeled. So we have the labels indicating the onset of a seizure, or at least where they think there is an onset, at least the onset. Right? As you can see here, this is denoted by the red vertical line at time step 10. And all right, so just a few details. In particular, we construct a graph on a time window of 1 second. Okay, that's what we decided. So 1 second of recording gives your graph, and then that's how you obtain your sequence of graph. This time resolution seems to be good enough for the problem that we are dealing with, because they are not interested in a millisecond timescale. Epilepsy is something that is well described at the second level. That's at least what they say. So the second timescale is good for in our case. Now, localization. So when we perform a prediction of the onset of a seizure, we at the same time provide a matrix, which is a matrix of weight highlighting the importance of different regions of this graph for what concerns the prediction itself, right? And that's called attention matrix, and a representation is shown here, where you have you have to think about this as a matrix of the same size of your graph, where these so the larger the weight, the more important is the edge of the node for the prediction. So we can, as I said before, we can characterize edges, nodes, which will be brain areas. Edges will be the relation between these two brain area, and at the same time also the time steps. But the time steps here are not represented. So all right, so we can perform a prediction and localization. We have the elements that we need, and we are performing some experiments on real data, but also on simulated seizures. Why? Because it's actually very hard to have ground truth information on the localization of seizures. So it's very difficult to understand where is the focus of a seizure. And they basically, I mean, our colleagues in Toronto basically are not sure where the focus is, and they rely on surgery. Basically, they, in order to understand whether where is the focus of a seizure, they intervene and they remove brain tissue. And if everything is fine after the surgery, they think that that was the right focus, right? Otherwise, no. So it's also a dangerous business, as you can understand. So it's very difficult to get supervised information, reliable supervised information. So we first are benchmarking the methodology on a controlled setting, where and the model that we have used is described in this paper, which is a fairly realistic model of seizure onset, where you can have any, of course, a network of any or a graph of any size. But in this case, we consider just a 3-vertex or 3-node network, where you have the in the pre-ictal phase, the activity is described by a fixed point, which is perturbed by noise, as you can see here. So the first 3 plots represent the activity. I'm not sure if you can see what's written here because it's not very high resolution, the projector. But so the first 3 plots here are showing the activity and the attention, so the weight that we give to the 3 nodes. Okay, the activity before the onset of a seizure, of the simulated onset of a seizure, is consistent with the behavior of a fixed point perturbed by noise. So basically it's like a constant behavior with some noise. As you can see, it's almost constant, and there are perturbations in all 3 nodes, right? They behave in the same way. At some point, basically, we increase the noise intensity, and there is something happens, which is called a bifurcation, and they start to oscillate, right? So the behavior is different. The change in behavior that I mentioned before, and this is also we think that our goal is to detect this change in behavior in the pairwise relationship between these nodes. So as you can see here, it's a bit difficult to understand what's going on here, but we don't have a very, at least right now, we don't have a very good way to represent this. But the red line is the onset, simulated onset of a seizure, and the first node that changes in behavior is the second one here that you see here, right? And as you can see, the attention related to this node is higher when there is a change than the others. Right? So the attention is higher exactly on the onset of a seizure. And then the next node which changes in behavior is this one. Okay, these nodes are connected, of course, but they are designed such that the onset starts in one node and then propagates. Okay, so the behavior changes in the different nodes at different time steps. So you can localize the onset. Okay, so second node is the first one, third node is the second, that changes in behavior, and last one is the first one. Okay, and as you can see, the attention, so these orange, green, and blue lines are consistent with this, with the design of the onset, right? It's not, maybe it's easier to understand what I'm saying from this plot here, the fourth from the top, and as you can see at the beginning, the orange attention is larger than the other two, then the green start to become larger, and then they are all the same because they changed, they all changed, so they are equally important. Okay, so and as you can see, the prediction, of course, it works because, as I said, they work together. When we predict a change, we localize the change. So in a control setting, it works. That's good because we can. That's a way to benchmark your methodology. And as I said, with real data, it's very difficult, and we basically have to rely on the output of a surgery. Now, that we are 10 o'clock. Yes. Okay. We have, there is a class. 5 minutes, right? 2 minutes. So I'll be, we are doing it also with real EEGs, and that's a bit messy, but it seems to work. And this is the EEG that is associated with a patient that had surgery, so we know which part of the brain they took off. So it seems to be consistent in this case, but we have to, of course, perform the simulations on more patients, and we need to evaluate the methodology better. All right. So as I said, we hope to finalize this part of the project, prediction localization, soon. But really, what we are interested in is control. So when we are able to predict localized seizures, we would like to react to this change in behavior and control the behavior of patients through neuromodulation. And we would like to come up with an automatic way to basically perform neuromodulation. And that boils down to designing a control strategy. That's something that is starting to become very important in neuroscience. It's called network control, where basically there is they try to figure out a way to inject inputs in different nodes. So your graph that is representing the brain, such that the state of the brain is modified or is directed to a desired state, right? So this is a very interesting and very challenging, of course, research area, and I think we will try to approach this problem of controlling a brain state through reinforcement learning, because it fits well within the context of graph neural networks that I mentioned before. And but really, we are that's something that's more of an idea, because we still have to work on control aspects. So thank you very much. Thank you very much.
Thank you for everybody's indulgence here. Thank you to Lorenzo for doing this and persevering despite technical problems. We'll post this on the website. I think we have to clear the room because there's a class starting, so no questions. Thank you very much.